Battery Charger Basics by Microchip. Welcome to the training module on Battery Charger Basics. Today's training outline consists of definition of battery chargers, battery technical terms and chemistries, applications, and Microchip's charger portfolio. A battery charger is a device used to put energy into a secondary cell or battery by forcing an electric current through it. Nowadays, the use of batteries as a prime power source for power devices is on the rise. As a result, a burden has been placed on the system designers to create sophisticated systems utilizing the battery's full potential. Each application is unique, but one common theme rings true: maximize battery capacity usage. A good battery charger is also able to extend battery life and monitor the charging process. A battery is a device that converts the chemical energy contained in its active materials directly into electric energy by means of an electrochemical oxidation-reduction reaction. The theoretical voltage of a battery is determined by the type of active material contained in the battery. The theoretical capacity of a battery is determined by the amount of active materials in the battery. It is defined in terms of coulombs or amp hours. The ampere-hour capacity of a battery is directly associated with the quantity of electricity obtained from the active materials. The capacity of a battery can also be considered on an energy watt-hour basis by taking both the voltage and the quantity of electricity into consideration. This theoretical energy value is the maximum value that can be delivered by a specific electrochemical system. When charging or discharging, the rate of a charge or discharge is often expressed in relation to the capacity of the battery. This rate is known as the C rate. The C rate equates to a charge or discharge current and is defined on this page. A battery discharging at a C rate of 1 will deliver its nominal rated capacity in 1 hour. Typical maximum rate of charge for a lithium battery is 1 C. For example, if the rated capacity is 1.7 amp hours, a discharge rate of 1 C corresponds to a discharge current of 1.7 amps. A rate of C over 10 corresponds to a discharge current of 170 milliamps. There are two types of batteries: primary batteries or disposable batteries, and secondary batteries or rechargeable batteries. Modern batteries use a variety of chemicals to power their reactions. Typical primary battery chemistries include zinc-air, zinc-carbon, mercury, lithium, and alkaline. Typical chemistries used in secondary batteries include nickel-cadmium, nickel-metal hydride, and lithium-ion, lead acid, and rechargeable alkaline. Among them, lithium ions have become the fastest-growing rechargeable battery chemistry in the marketplace today, especially for handheld battery-powered applications. As today's devices need more and more energy, they are turning to the lithium ion because it has the highest energy density by weight and volume. Portable electronics devices have dramatically changed the way people live and work. They play an important role in a person's daily life, from everyday tasks to entertainment. With the emerging technologies that are available today, portable electronic designers are trying to integrate more features into smaller and lighter form factors, while extending the system runtimes. These devices include media players, GPS, keyboards, Bluetooth devices, handheld power tools, and wireless headsets. A high-performance charger is required to recharge any battery quickly and reliably. The following system parameters should be considered in order to ensure a reliable and cost-effective solution. The charge current needed depends on the size of the battery being charged. If a battery has a 200 milliamp hour capacity, then having a 1 amp charger is too much, as its peak charging is 5C. If you remember from the previous slide, typical lithium-ion batteries are not charged at rates above 1C. This slide illustrates two graphs that depict the capacity of the battery versus the charging voltage, and the capacity loss versus undercharged voltage. A small decrease in charging voltage results in a large decrease in capacity. From the chart on the right, we can see that at a slight undervoltage charge of 1%, the capacity will lose 8%. It can be concluded that the lower charge voltage leads to smaller overall capacity, but allows for more charge or discharge cycles. Poor voltage accuracy leads to decreased capacity. Microchip offers a complete line of lithium-ion, lithium polymer, lithium iron phosphate battery chargers. The charge management controllers provide a reliable, low-cost and high-accuracy voltage regulation solution with few external components, in an effort to further reduce the size, cost, and complexity. In this slide, we illustrate Microchip's battery chargers. This table lists the single-cell chargers. In this slide, we list the dual-cell chargers. Microchip's battery chargers offer internal or external pass transistor options. The integrated pass transistors allow smaller solution size. Some chargers utilize an external pass transistor to allow great design flexibility and high power charging level. Some devices like the MCP73837/8 and MCP73871 are designed to select the USB port or the AC adapter as the power source automatically. That means that they allow two different charging profiles depending on the power source. If the AC adapter input is not present, the USB port is selected. If both inputs are available, the AC adapter has first priority. Most of the time, batteries are designed to be recharged while the devices are still in the operational mode. Microchip's battery chargers enable this function. The input power should supply the system load and charge the battery when a battery is present in the system. When the input power source is removed, the system is supported by the battery. When the system load and the battery draw more energy than the supply can offer, the system load takes priority over the battery charger. These chargers are also available with an overvoltage protection. In case of voltage spikes on the input, the charger shuts down to prevent damage to self or other devices. In order to supply world-class portable devices, most of Microchip's lithium-ion battery management controllers are equipped with thermoregulation, reverse discharge protection, safety charge timer, and integrated current sensing. An internal undervoltage lockout circuit monitors the input voltage and keeps the charger in shutdown mode until the input supply rises above the undervoltage lockout threshold. The thermal shutdown is a secondary safety feature in the event that there is a failure within the thermoregulation circuitry.